In this video, we're going to learn how to evaluate and identify exponential functions. So for these first examples, we're going to approximate each number using a calculator and express our answer rounded to 5 decimal places. So I'm going to use a calculator, and if I wanted to plug in 2 to the 1.4 power, I would put 2, up arrow key 1.4, and I would record 2.63902. Now we'll do these for several of them because I'm actually using an approximation for the square root of 2. And I'm going to do them incrementally so you can see how accurate it gets leading up to 2 to the square root of 2 power. So if I did 2 to the 1.41 power, you'll see how much it changes. We get 2.65737. You already see here it changed by about 2/100ths. 2.414. Oh, 2 to the 1.414. We get 2.66475. And lastly, we can also do 2 to the square root of 2 power, which would be 2.66514. So you'll see just small changes in the exponent can definitely change your output by a good bit. So make sure you're being as accurate as you possibly can with your exponents so that you can get a more accurate answer. So now let's look at pi. So the difference between using 3.14 and pi, let's see what happens. So let's do 3 to the 3.14 power. That gives me 31.48914. But when I just add one more decimal place following pi, I get 3 to the 3.141, which is 31.52375. So you can already see a pretty big change just between the two of them. And usually the bigger your base is in comparison to the previous example, you'll usually see those bigger changes. So I want to be as accurate with these exponents as you can. Let's look at 3 to the 3.1415. I get 31.54107. And then 3 to the pi power is 3.31.54428. You're definitely going to see here, like the more decimal places we used, the more like places we got past the decimal point that were accurate to the final answer. You'll see here the first one only gets like the whole number correct, but as I added one more decimal place, I got the 10th place correct. Then I added another decimal place in the power, got the 100th place correct, and then so on. If I kept being more accurate with my power, I would hone in on this number. But you can see here that there can be a very stark difference between using a rounded version of a number than the exact version. Now, next I want to go over is some properties of exponential functions. So, an exponential function in its basic form has an initial value times a growth factor to the x power. So, it'll have some number it starts at, and then it'll be multiplied by a particular number over and over again to change it. And I'll show that in a few examples in a minute. But one key factor of exponential functions is that if you put the consecutive outputs in a ratio, they'll always equal whatever the growth factor is. So meaning if I took f of x plus 1 and f of x, meaning the x inputs are just one apart, they're consecutive, and I put them over each other, you'll see here I changed the x into x plus 1 and the x into, I guess, x. put them over each other, I cancel out the c's. I subtracted the exponents due to the law of exponents for division. You would subtract them. And it was just a to the 1, which is just a. So that's a really good way you can find your growth factor just given a table of information. So now for these next few, we're going to identify whether the function is linear, exponential, or neither. Now, I went over how to detect if it's exponential, but let me go over how to detect if it's linear. And that just means that its average rate of change is constant. Now, what is an average rate of change? That is just your slope that you would find between 2 points. So in this case, I would do y2 minus y1 over x2 minus x1, so that would be 2 minus 5 in the top, over 0 minus negative 1, which would give you negative 3 over 1, which is negative 3. A quick way you can do this, if you recognize that all the x's are going up incrementally by 1, is just to ask yourself, how much does it change from 2 to negative 1? Well, it goes down 3. That would be its slope. If I did the same thing from negative 1 to negative 4, I would get negative 3. And then from negative 4 to negative 7, I would also get negative 3. The fact that these values are constant, these average rates of change, means that we have a slope, causing it to be a line. Now, if it's a line, can it also be an exponential function? Let's look at the ratio of consecutive outputs. So I'll just be putting the next value over the former. So in this case, it would be 2/5, and then negative 1/2, then negative 4 over negative 1, which would be 4, and then negative 7 over 4, negative 4, which would be 7/4. But you'll see here, none of these are consistent, meaning that it's not an exponential function. These values would be the same every time if it was an exponential function. So in this case, since the average rates of change between every point is negative 3, this is a linear function. And I can write the equation by using the form y equals mx plus b, where m is your slope, so in this case, negative 3x, plus your y-intercept, which is whenever x is 0. Also you can also think of it as an initial value, like you saw over here. So y equals negative 3x plus 2. So those average rates of change ended up being our slope, as we saw from our slope equation, and at 0, 2 gave me my y-intercept of 2. Let's try this again with the next example. So again, using that slope, as I go from 32 to 16, it goes down by negative 16. It goes down by 16. 16 to 8 goes down by 8. 8 to 4 goes down by 4. And from 4 to 2 goes down by 2. You'll see here, none of these are constant, so this is not a linear function. Ooh, I forgot to label that here too. I forgot to label it as linear for the previous one. Now, if I want to know if it is an exponential, I have to look at the ratio of its outputs. So I'll put 16 over 32, which simplifies to 1/2. Put 8 over 16, which simplifies to 1/2. 4 over 8, which simplifies to 1/2. And 2 over 4, which also simplifies to 1/2. So since these are constants, I'm dealing with an exponential function. And the way you write its equation out is you put y equals, and then c would be its initial value, which is wherever x is 0. So in this case, 16. So I have 16 times the growth factor, which we found is just the ratio of the consecutive outputs, whatever that constant number is. You put inside parentheses and raise to the x power. And that's how you find that exponential function. So what it's saying is we start with 16 and we just multiply by 1/2 to get the next number every time, over and over again. The reason why it goes up backwards is like when you go backwards, you would divide by a half, meaning you would multiply by 2. Now, lastly, let's look at this example. We have from 2 to 4, that goes up by 2. From 4 to 7 goes up by 3. So those slopes between these points are 2, 3. Then from 7 to 11, it goes up by 4. So slope of 4. 11 to 16 goes up by 5. So a slope of 5. None of these are constant, so it's not linear. Let's look at the ratio of consecutive outputs. Put 4 over 2, which gives me 4. 7 over 4, which is just 7/4. 11 over 7, which is 11/7. And then 16 over 11 is 16/11. None of those. 4 over 2 is not 4. That is 2. None of these are constant, so it's not exponential either. So we say this is neither situation. Now, this could be some other type of function, but this is not linear, nor is it exponential. And that is how you evaluate and identify exponential functions.